Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
He's been here for a longer time and all know him, so I don't he will probably explain what M/G means. I know it, but I leave it to him. And he will talk about dispersion of mass and the complexity of randomized algorithms.
This is a joint work with Luis Rademacher, who's at MIT. So let's see, what do I mean by this dispersion? Well, roughly speaking, it'll take me a few minutes to adjust to the speed of the machine.
Know that,
right, the notes on the back. Well, by dispersion, I would like to mean how spread out a distribution is. Here we have some density function on the real line, and it's a very common question, one that I would guess everyone in this room has worked on. How do we prove that this distribution is concentrated around some point? Some of the experts are here. What I want to do in this talk is work on sort of the opposite question, which says, well, you'd like to show that for any point on the line and a random point x from this distribution, the point is far from the given point. So the random point is far from the given point. X minus a is large. Well, how do we measure this? So one classical notion might be variance. Right? Variance measures the expected distance, at least square distance, of a random point from, well, in this case the fixed point being the mean, but certainly that gives a lower bound for any point. The trouble with variance is that large variance does not imply large dispersion. I mean, you could have large variance because most of your probability is concentrated, while a little bit, an exponentially small fraction, is spread out or far away. That can blow up your variance. What we want here is a notion that's more like this. So the dispersion of a one-dimensional distribution, and one can generalize naturally to higher dimensional distribution, is the following. It's the smallest interval, it's the smallest interval which contains a 1 minus p probability mass. Okay, so a p fraction of the probability is dispersed outside this interval for sure, no matter where you pick this interval. Okay, and so what does this give us? Suppose the distribution has dispersion this, then with probability p for a random point x, the distance from any given point a will be at least this dispersion divided by 2. Since you will be outside the interval with probability p, pick the interval centered at the point you care about, and you're. Now later on I'll point out that this, I haven't seen this specific definition anywhere. It's naturally motivated by complexity. We'll see that in a couple of minutes, and it seems to have its own nice set of operations. Not as clean as variance, but still quite interesting, it seems. Now the other end of this talk is randomness, which we're all familiar with, and leads to simpler, faster, nicer algorithms. And a fundamental question, complexity, is this essential? One way to formalize that is what we can solve in polynomial time deterministically, the same set as what we can solve with randomness. I don't have any special insight on this at this point. However, I'm willing to make a bet that the answer is yes, and that we'll know by the year 2100. And I will wager.
And you'll be around to pay off.
Well, if I am, I'll pay you. Yes. and if you are too. I mean, yeah. Okay. Well, so the question here is, does it provably reduce complexity? Okay. Now, and the answer in the model of computation with arithmetic circuits is we don't know. We really don't know. What is a randomized algorithm? Well, one way to think of it is.
Is your answer yes to p equals BPP, or is it essential?
The answer is yes to p equals BPP. Yes. although you could convince me otherwise. But yeah. So the output of the algorithm, let's say it's an algorithm that computes a number, is a distribution. Since it also takes as input some random bits, it gives you some output, but really the output is from a distribution. Now, to prove that the algorithm works, you want to show that this distribution is concentrated around the right answer, whatever is the right answer to this function, if it's computing a function. And to show that the algorithm fails in a certain number of steps, you'd like to show that this distribution is dispersed. In fact, exactly the type of notion I've defined. You want to show that there is a small probability with which it's away from the right answer. Okay. Now, there is there are very few instances where randomness provably helps, and one particularly nice one is the problem of computing the volume of a convex body. Okay, so you have a convex body in n-dimensional space, and we'd like to estimate its volume. Now, the way one has to be careful about how this body is specified. It's not given explicitly, but through an oracle. Again, probably many of you are familiar with this, but let me spell it out. That the oracle lets you input any point x in space, so an n-dimensional vector, and answers yes or no to the question whether the point belongs to the set. In addition to this oracle, you also have weak bounds, numbers, small r and little r, which sandwich the body. So there's a small ball contained inside and a big ball containing the body. These numbers could be exponentially small and exponentially large. We need some guarantee that the body is contained in these. Now, in fact, for the rest of this talk, I will assume that the ratio of these numbers is 2n. It's linear in n, so we only have one parameter, the dimension of the space. This can be achieved by appropriate transformations, which will not be useful to think about in this talk. So we will actually assume that we have this body, this convex body that contains a ball and is contained in a ball that's not much larger, by a factor of 2n at most. Okay, so what is the complexity of this problem? So about 20 years ago now, Elikish and then refined by Barani and Furedi proved that any deterministic algorithm that uses at most n to the a oracle calls. By oracle calls we mean the calls to this oracle, the membership oracle. That's the only point of contact with the convex body. Cannot approximate the volume to within this exponential factor. So if you use for any fixed a, any polynomial time algorithm, that would the factor of approximation that you can guarantee is no better than n over a log n to the n. So it's really poor, and there's a trade-off there. So to get a constant approximation, for example, you'd require a to be n over log n. Now, this is not a very, in case you haven't seen it before, it's a simple idea, and let me just quickly sketch it. Imagine you're the algorithm and I'm the oracle, and I'm going to the body. So you keep asking me questions. In fact, I tell you in advance the body is contained inside this unit ball. Okay, so you keep asking me these questions, and the way I'm going to answer is if it's in the ball, I say yes. If it's outside the ball, I'll say no. Okay. At the end of a polynomial number of questions, you know that the body contains the points that you asked inside the ball, and in fact, it must contain the convex hull of those points. But after that, it could be any body that lies in between that convex hull and the full ball. The ratio of those volumes is exponential in n for any polynomial number of points, and that's it. That's the whole proof. So you really have no idea between those what it is. Well, that's the whole proof with a slightly weaker factor. To make it this factor, you need to be a little more careful. Now, on the other hand, rather amazingly, paper by Dyer, Fries, and Cannon shows that a randomized algorithm can take any epsilon delta as input, and with probability at least 1 minus delta computes an estimate v, which is a 1 plus epsilon relative approximation to the volume in time that's polynomial in n 1 over epsilon and log 1 over delta. I will start ignoring the probability factor because that drops exponentially the probability of error, but it's polynomial in n and 1 over epsilon. The original algorithm had an exponent of 23 on the n, And the most recent, the current fastest algorithm is n to the 4 over epsilon squared. I never imagined I'd gloss over the sequence in between, but this talk is really about something else. But what I want to tell you is that if there is a wonderful sequence of papers here, a couple of the people, Latsi and Mickey are here, both here, with techniques that extend to many different problems besides just the volume problem. I won't go into that, but let me just say that it's turned into a wonderful subject. The current best is n to the 4 over epsilon squared. Now this leads to the question: how low can we go here? Right? What's the right answer? I mean, there was n to the 23, 16, 10, 8, 5, 4, and a couple of 10s. So, do you want to guess?
You have to tell the sequence.
Sorry? Yeah, so, and actually, let me just tell you that this algorithm is conjectured to be n cube. One could get it down to n cube if a certain geometric conjecture is true. This one by Ravikant, Latsi, and Mickey, which basically says that to partition a set into sides of equal volume, you can approximate that with a hyperplane. Well, to partition with minimum surface area, you can instead approximate with a hyperplane. It's called the hyperplane conjecture. It's not clear if that's true, but if that conjecture is true, this algorithm would actually be n cubed. So there is some hope that the algorithm could be n cubed. So what's the best possible? That was the motivation for this talk, and I'll get to that in a second. So how do we prove lower bounds on a randomized algorithm? Now again, probably most of you are familiar with this, the content of this slide. Let's imagine a matrix whose rows are algorithms and whose inputs are possible convex bodies. Now I can't really write down a matrix, but let's say this is such a thing. Now algorithms that use at most m oracle queries of complexity at most m, and those are convex bodies which satisfy whatever roundness condition that we said must exist. So the ratio of those radii is bounded, and the entry here is 1 or 0 depending on whether the algorithm A fails on input I or not. Okay, so this is just encoding whether the algorithm in this many steps correctly answers the input, which for us correctly just means, let's say, estimate to within a factor of 2. Okay. Now a randomized algorithm is simply a convex combination of deterministic algorithms, so it's a probability distribution here. And to prove that a randomized algorithm fails, we need to show that no matter what distribution you take here, there is some input, one for every different distribution, on which the probability of failure is high, which just means 1 over polynomial. Okay. Now Yao's observation, which is a very straightforward thing, is that let's say I also pick a distribution on inputs, then the joint expectation doesn't change if I reverse the order in which we take the expectation, whether you take it first over the inputs or first over the algorithms, and therefore the probability that a given distribution, a given randomized algorithm fails on some I, so the highest one, must be at least the probability that some deterministic algorithm fails on this distribution. So that's the simple observation. And so in order to prove a lower bound for a randomized algorithm, all we need to show is some distribution on inputs on which every deterministic algorithm fails with some probability. Right, so this is the easy direction which we need, and in fact under some mild assumptions on the distributions, this is an equality. That's von Neumann's min-max. Yao had the insight to use it for complexity lower bounds, which has turned into a. So what here are some results that I will present. So here's a warm-up problem. There's just one single unknown vector A in an n-dimensional space, and in fact I tell you that the coordinates of the vector are between -1 and 1. The way you can access the vector is to ask, think of the vector as a normal to a half space, and you can ask to the half space A dot x less than or equal to 1, so it's a distance 1 over length of A from the origin, and you ask for a point x, is it in the half space or not? That's it. So there's a half space out there parameterized by A, and for any given point it tells you in or out. The problem is to find the length of A, or estimate the length of A. Okay, this is some toy version of the volume problem. Now it's easy to see that roughly n log n calls are enough to get an arbitrary close approximation, because well, what you can do is shoot a ray in any direction and figure out where it hits the half space. By that I mean do a binary search, ask a point x, are you inside or outside, and then keep asking in a binary search fashion till you get an equation. So now you get an equation on A. Ask n such linearly independent directions, you get n equations, solve for A, and that's it. Now there's a log n because you have to do this binary search, and really log n over epsilon depending on how close you want to come to the length of A. Now suppose in fact that A is random, meaning I pick it uniformly in the range -1 to 1, each coordinate, independently and uniformly. Now then, just from concentration, it's the length squared is the sum of these squared lengths of independent variables. If you just guess the mean, you'll be within a constant. This 1 represents a constant, but you'll be within a constant already, okay, because the deviation will be a constant. What we can prove is that if you want to do slightly better, let's say you want to now find the length to within plus or minus 1 over root log n additive term, then you need to make n oracle queries. So to get within a constant you don't need any queries, just guess the mean. And to get slightly better, 1 over root log n, you need to make actually n minus 1 queries. The constant is 1. And so one way to think of it, when I gave this talk at the IAS, Ivy Vigdisson pointed out that this is in the spirit of what are called hardcore predicates in cryptography, and here's one way to think of it. So this number that we want to guess the length is already in some constant range, just from concentration, and now we want to break this up into intervals of length 1 over root log n and pick the right one. Okay, so the number of intervals is only root log n, which means the number of bits you need to specify the interval is only log n. So you only need log n bits, or you're trying to get log n, yet you need to ask n bits of information, which is are you in the half space or not, which is 1 bit at a time. So to get these log n you need n bits, and you can view these log n as a hardcore encoding of the full thing. Anyway, so this is the warm-up result. Now the main results are the following. We're actually going to have an unknown matrix A. So the entire matrix A is unknown, and the matrix represents a parallelepiped. Okay, so the rows are the normal vectors to the facets of the parallelepiped, and so what is a membership oracle for this parallelepiped? You just want to ask for a point x whether each row in a product with x is between say 1 and -1. Okay, so the facets of the parallelepiped are a1 dot x between 1 and -1, a2 dot x between 1 and -1, and so on, where a1, a2, n are the rows. And so the membership oracle is exactly this, whether the infinity norm of ax, so the largest component of ax, is smaller than 1 or not. So that's checking whether it's in there or not. So that's the matrix. It represents the set of convex bodies exactly, which are parallelepipeds. And here are two problems. Estimate the volume. That was the first problem we started with. But what is the volume in this case? It's 2 to the n times the determinant of A inverse, which is the same as estimating the determinant of this matrix. So volume for this special class is simply estimate the determinant. And here's also a natural question, and in some ways, well, it leads to nice things as well. The product of the lengths of this matrix. Okay, so here are two questions. Estimate the determinant, estimate the product of the lengths of this matrix. We saw the special case where we have only a single row needs n queries to do better than the trivial approximation. So the theorems are that there exists a constant C, independent of anything, such that any randomized algorithm that estimates determinant of A to within a 1 plus C factor, relative factor, must use n squared over log n queries. So to get 1 plus C, you must use n squared over log n queries. And well, the probability of success for the randomized algorithm, I have not said it, is 1 over n. So any randomized algorithm that finds the determinant within 1 plus c with probability at least 1 over n must use.
Also have A is a random matrix or not yet? It's just unknown.
Well, I have put it as unknown for the moment. I mean, this statement doesn't say anything about the input A. In the proof, we will use a random distribution on A.
Estimates a probability with if it estimates correctly with probability at least 1 over n, or
by a simple trick, you can make that any polynomial, which is this idea of suppose it.
The error
or so 1 minus 1 over n.
Yes, 1 minus 1 over n. So if that's right. Sorry. Excuse me. The failure probability 1 over n. So the randomized algorithm correctly estimates this with probability 1 minus 1 over n to the epsilon. Yeah. Right. Yeah. If you wanted to make it constant, then we'd have to add another log here, which. Yeah. Just a log. Yeah. If you want constant probability, it's n squared over log squared. And same result for the product of the lengths, except that the approximation factor is not a constant, but 1 plus 1 over log n. Okay. Now, I would like to note at this point that this is nearly optimal for this class of inputs. And so for these problems with determinant and product of lengths, this is in fact nearly the best possible, because you can actually solve the problem in n squared log n queries. Here's what you do. You can actually figure out the entire matrix in n squared log n queries. So you can compute any function of that. What you do is the following. You pick a set of n directions which are very close to each other, but in a random direction, like a little cone, and shoot them. Now with high probability they will hit the same facet, whichever that is. So you get equations for that facet. You solve for that row of the matrix, and now everything else is a subproblem, because you know the answer to that problem, and now you all ask your queries orthogonal to that, and you continue. So you get with n log n queries, you can get one row of the matrix at a time. So in n squared log n, you can solve the whole problem. So with this class of bodies, you can't prove a better lower bound. And for these problems, determinant and product, it's optimal. For volume, it establishes an n squared lower bound. Just to recall, the upper bound is n to the 4, and conjectured to be n cubed. So I will now the techniques used here actually are somewhat indirect. They have some interesting connections to convex geometry. So I'm going to start at that end and relate it back to how we prove these lower bounds. So these are the results as far as lower bounds are concerned. Now let me make a different start, and we'll come back to this point where we end up proving these theorems. So the specific aspect of convex geometry that I'm interested in is motivated by the following two conjectures. Perhaps some of the nicest conjectures in the field, well, the nicest ones I know. So a convex body is said to be isotropic. It's a normalization. So the classical definition asks that the volume of the body is 1, which is some scaling. The mean is 0, which is the translation, and that the coordinates are uncorrelated. So the expectation of xi xj is a constant if I equals j and 0 otherwise. So and now alternatively the expectation of the covariance matrix. The covariance matrix is the identity. Now there is an alternative definition which is often much more convenient, and that's to make the alpha k 1 and remove the volume condition. Okay, but that's, as you can see, is just going to be a scaling of this. In case you haven't seen this before, this isotropic position can be achieved for any convex body by an affine transformation, a translation for the origin, and then a rescaling to get the covariance to be the identity. Okay, now assuming the body is isotropic, here are two conjectures. That for any isotropic convex body, this alpha k is actually bounded by a universal constant. This is the isotropic constant, and it implies something called a slicing conjecture, which is very nice. It says that for any convex body, there's going to be at least one section whose volume is comparable to that of the whole body, and that's implied directly by this. And here is another one. It's a bit more technical, but roughly what it says is that the variance is bounded by the square of the expectation divided by n. Now you don't have to spend too much time on this. Here is an implication of both of these which occurred to us independently, which says that for any isotropic body the variance of x squared is order n. The expectation of x squared is order n because it's the sum of the expectations of each of the coordinates which are conjectured to be constants. And what this is saying is that the variance is also order n. Now I'll give a couple of examples to say what this means. The reason for this conjecture, no problem, is that in fact if it's true, some natural random walks would be faster on isotropic convex bodies. So that's the reason it came up previous to this work. But let me just motivate the actual conjecture. The variance of x square is n, is what we're saying. So here are a few examples. So in the ball, the isotropic ball has radius roughly root n, and most of the volume is going to be close to the boundary. In fact, it will be contained within the radius times 1 minus 1 over n. A constant fraction of the volume is contained right there. And so the length of a random point lies in between root n minus 1 over root n and root n, since the radius is root n. And so the length squared is basically only varies in a constant interval. And so the variance is a constant.
There's no root there, I guess.
Oh, the length squared, there is no root, that's right. Yeah, there's no root in this. I just square both of those. So for the ball, the variance of x squared is actually just a constant. But it is also the body that minimizes this variance. As you can, you're trying. What is variance of x squared? Your variance of length of x would be simply how much the length of a random point varies, and we're looking at the length squared of a random point. So you'd like to pack everything as close to a single radius as possible, and that's achieved by the ball. It's no surprise, and you can prove that. Now at the other end, as far as we know, are the Gaussian and the cube. Let me just look at the cube. So make it volume 1. It's this, and it's actually isotropic. And it's a little exercise to prove that it's isotropic, even though it doesn't look like that necessarily. Now what is the variance of x squared? Well, the coordinates can be viewed as independent distributions. Each coordinate is just uniform in the range, say 0 to 1, and so the variance is the sum of the individual ones, and each one is a constant. It's the uniform distribution on an interval of constant length, so it's some constant times n. So the variance of x squared for the cube is some constant times n. It's also the same for the Gaussian, up to constant times n, and the conjecture is essentially saying that this is the worst possible situation for any convex body, and in fact for any log concave function. Okay. So in terms of how large a band you need to capture most of the, how large a torus you need to capture most of an annulus, to capture most of a convex body, well, it's whatever is needed by roughly the cube. Yes?
Is the tetrahedron no worse than the cube?
Up to a constant, yes. So you will see actually in a second. That's a good question. Not exactly the worst, no. Not exactly the worst. I don't think it will be as symmetric. Yeah, I think. Yeah, but the comment is correct in the following sense. In fact, so here is one of the tools that we use for the proofs of the lower bounds. Take any convex polytope with at most n to the k facets. So the number of facets is bounded by a polynomial in n. Volume is 1, and it's contained in a ball of radius some polynomial n to the cube. Then the variance is some constant that depends only on the exponents there, k and q, times n over log n. So for any convex polytope that's contained inside a ball of polynomial radius, the variance is almost as bad as it is for the cube. In particular, it's really far from the ball. It's another way to think about this. Is another way in which the ball really differs from a polytope with few facets. A ball has variance 1 in x squared, whereas a polytope with a polynomial number of facets has variance n over log n, almost the highest possible conjecture. So and if we look at the isotropic case, so this is saying that any isotropic convex polytope with a polynomial number of facets gives you n over log n, because isotropic will guarantee that it's contained inside a ball of radius n to the 3 halves.
So it is known that for any convex body, if you take a random direction, then it behaves like a Gaussian. Its estimates of the error are not good enough to derive what you want.
Yeah, so this is there are many results in this direction, but this sort of behavior like a Gaussian is not yet, is still largely an open problem. So recently there was some progress which says that this variance of x squared that I'm describing here, so trivially it's n squared, but it actually is no more than n squared over log n. And this can be viewed as a central limit theorem for this, because it's slightly better than the square of the.
So this is what would follow from this result of Clark?
Yes, it is his result. This is what he did. This is exactly what he proved.
Okay.
Yeah, yeah. Unfortunately, the technique there will not go much further, because basically he projects to a log n dimensional random section, and there some it actually focuses in, and you can prove not only variance but a tail bound on the distribution of x squared after the projection. Enough to save log n. It's not trivial, but that yeah. So anyway, so it's the lower bound of n over log n. Now I will just briefly mention that the proof proceeds by an induction, and sort of the main case is when the origin is contained inside the body. Now you might wonder, why can't we just assume the origin is contained inside the body? You're trying to prove that the variance of x squared is large, and so you look at the body, which you look at something that minimizes it. Now if you were trying to minimize the expectation of x squared, then you'd choose as the origin the centroid, because that would minimize the expectation of x minus this point squared. For the variance, that's not true. In fact, you can construct bodies where the variance of x squared is minimized by points that are arbitrarily far. So this assumption that the origin lies inside in order to minimize is not valid. Nevertheless, it turns out this is the main step, and what we can do is an induction which expresses the variance of the entire polytope in terms of the variance of the cones induced by the facets, and then the variance of the cone as just the variance within the facet plus a little term that we get at each step of the induction. So I won't say too much more, since I want to get to the lower bound, but it's an induction that involves the dimension, the number of facets, and the volume. And as you go along, you get a constant for the first n over log n expansions of this recurrence. Now it is quite possible that the answer is actually just n for isotropic polytopes with few facets. I don't know. Here we proved for any body which is contained inside the ball. So how is this useful for proving lower bounds? So let me remind you that we were asserting that in order to estimate the determinant of a matrix and of an unknown matrix given by this membership oracle, or the product of the lengths, we need n squared over log n queries. So what do these distributions have to do with the determinant or the product of the lengths? So I'll first work with the product of the lengths problem, because that's a little easier at this level, and then just mention the technique that we need for doing the volume lower bound. Okay, so any questions at this point? So the input. So what do I have to do here to prove a lower bound? I have to give you a distribution on inputs by Yau's lemma on distribution matrices, so that even after n squared over log n queries, if you look at there is going to be some surviving distribution. As you ask queries, it restricts the distribution. You know more and more about the matrix, but you still have some conditioned distribution. And so for that condition distribution you'd like to show that there is still a large dispersion. Okay, that's what you need. So the input distribution here is a random matrix R, and the entries are independent, uniform in the range -1 to 1, just as we did for the single vector case. And what is the oracle doing? Again, just to remind you, on any point x, it checks whether Ri dot x is between 1 and -1 for every I. Okay, it checks whether you're inside the parallelogram. Now I'm going to modify this oracle slightly, providing extra information. So any lower bound we prove here applies to the other oracle also, but this will be useful. On the yes answer it stays the same. On the yes answer you know that for every row Ri dot x the absolute value is less than 1. On the no answer, in addition to no, we also get the smallest index j. Okay, there's some ordering, the smallest index j such that R j dot x is bigger than 1. Okay, so the first point so the first I minus 1 are still less than 1, and j is the first one where it's greater than 1. Okay, so that's a little bit more information, right? Instead of 1 bit, the possible outcomes are 2n plus 1. Okay, now the claim that we want to prove is that any deterministic algorithm that estimates the product of the lengths to within a 1 plus or minus 1 over log n, c over log n factor, on most of the distribution, 1 minus 1 over poly n of the distribution, needs at least n squared over log n queries. So that's. But now we're down to we're only looking at deterministic algorithms. Now you can view a deterministic algorithm as a query tree or a decision tree. Right? The root represents the first query. The algorithm makes a query for some point. You get one of 2 and 1 plus 1 possible answers. Depending on the answer, you ask another query, and so on. So the algorithm is adaptive, of course. It can ask questions depending on the previous answers, and you ask h queries in this picture. So let me define PL to be the set of matrices. So at the root is all possible matrices, and in fact the uniform distribution on them with entries in between -1 and 1. At a leaf L, let PL be the input matrices that are consistent with that path, so with the set of queries. Now what is the structure of PL? Initially each row of a matrix is picked uniformly from a cube. Each entry is picked from an interval. Let me think of each row as being picked from a cube. Now as you make more queries, what happens? Let's say you make the first query, you ask for some direction q, is r dot q less than or equal to 1 in the infinity norm, and let's say the answer is yes. So in the direction q, then you know that the actual instance that you're getting must lie in this band for every row, because in particular the yes answer implies that Ri dot x is less than or equal to 1 dot q. Okay, so that's for the yes answers. Now what happens if you get a no answer? Well, on the no answers you also get the index of the first one that's violated. So you know that it's a yes for up to the I minus 1. So let's say the next query is q1 or something, it's a yes for this up to some point, and for this it's a no. So for the no it lies on this side. Okay, so that's the no answer. All I'm doing, by all the modified oracle is doing is, well, what is it doing? We'll see in a second. So, and then for the rest you have no information. Could be yes or no. So the point of this is that with the modification, the distribution, the condition distribution, is still a product distribution. Okay, the first row is picked uniformly from the intersection of whatever constraints we got through the first h queries, the second row from whatever we got, and so on. So the modification is maintaining that the distribution on the matrices is independent choices from different distributions for each one, where each one is a convex polytope still. And how many facets does it have? Well, we started with a cube which has 2n facets, and if we ask h queries we get at most, well, that should be 2h facets. Okay, so that's the thing. So that's the structure of PL. Actually looks like a product set, and it's uniform on its support. Okay, now with this observation we can do most of the proof. So let's look at this tree, and the total volume of all the leaves is just the volume of these cubes. So instead of doing probability, I'm looking at volume, since it's a uniform distribution, is 2 to the n squared. It's critical because that's 2 to the n for each cube. Cubes are between -1 and 1, 2 to the n, product of n of them. And so if I go to L leaves, then it's 2 to the n squared over L. And the reason I'm doing this computation is to go down to a depth h where most of the leaves still have volume at least 1. Okay, we start at volume 2 to the n squared. Up to what depth can I go so that most of the leaves still have volume at least 1? And all I'm asserting is that you can go down to depth about n squared over log n. And the reason is that the degree of the tree is 2n plus 1. Right, 1 if you get the yes answer, and 2n if you get the no answer, because you get no, you get the sign of the violation and which inequality, which is the first, we get one inequality, one of n possibilities. So if you go down to this depth, the average is still, with probability at least half, not the average. Half of the volume is in leaves whose volume is at least 2 to the n squared over 2. So it's only gone on by 2 to the n squared over 2, which means that actually, since this volume itself is a product of volumes, being a product set, half of those regions must have large volume, and all we're asserting is the volume at least 1. So if the volume is 2 to the n squared over 2 and it's a product of the volumes of n regions, well, n over 2 of them must have volume at least 1. The simple pigeonhole. And now we use the lemma that about the variance being high for regions of volume 1, because these are regions that have volume at least 1 and have few facets, only 2n plus 2h facets, which is order n squared right now. So first we prove that the variance is actually high, and that's just looking at the variance of the product of the lengths divided by the expectation squared. Now this variance is 1 plus, I'm just writing down the fourth moment minus 1, and so a weak lower bound is the sum of the individual ones, sum of the individual ratios of the variance to the expectation squared. And then now look at this summation exclusively for those regions where the volume is at least 1, because for those regions we know that the variance is at least n over log n times some constant, and the expectation is at most n, because during the entire process in fact the maximum is at most n, because everything is contained in a unit cube to begin with, so the length is at most n. So this denominator is always no more than n. The numerator for at least n over 2 terms is at least n over log n, and so we get that the ratio is 1 over log n. So the variance is at least 1 over log n times the square of the expectation. Now that's the variance. To prove that the algorithm fails, we would need to show that the dispersion is large, that with some probability it's large, and that's not entirely trivial here, because the support is exponential. I mean the possible value of the product of the lengths is in a range that's n to the n size. I mean, sorry? No, it's not. The distribution on the length is not log concave, but its distribution function is log concave. The density is not log concave. No, it's not. So if you look at the length distribution of a point, from a random point from a convex body, it's not something that goes up and down. It actually can go up and down, and it can do that, the density function. However, if you look at its distribution function, which is what is the total mass contained up to distance x, up to distance t, that is a log concave function. And that fact is quite useful in proving this. Now I'm going to skip over this calculus of dispersion, which allows us to establish that the dispersion is large, but basically you get some inequalities for the sum, the product, and most importantly the decomposition. These are straightforward inequalities which say that if you want to prove that the dispersion of a distribution is large, then you can also look at a subdistribution, and that implies a lower bound for the full distribution. So I will skip over this part, but let me go to the volume now. Is that okay, or do you have any, unless you have specific questions there? So going from the variance to dispersion is a non-trivial step. One observation is that the distribution function is log concave. It goes up in a smooth manner, but then also that you can compose the distributions from different RIs to add up to roughly speaking add up the dispersion. And now going back to volume, which is a problem that motivated everything, the distribution we'll use on again I'm going to pick a distribution parallelepiped, so matrices, but in this case we'll pick each row uniformly from the ball of radius root n. So it's not each coordinate independently, but each row uniformly from a ball of radius root n. So for this original matrix itself, for this random variable, the determinant of R varies by a polynomial in n factor. Its variance and its dispersion are in fact n squared, and that's a classical fact. Now that's originally before we ask any queries. Now what's happening as we ask queries, again looking at the modified oracle, well initially it's a product of these balls, right? Each row is coming from a ball. As we ask queries, the yes answers restrict it to some bands, the no answers restrict some to bands and some to half spaces, and so on, but you still maintain the product set of distributions. That part is common to the proofs. And the question now is, after a certain number of queries, does the determinant lie in a small range, in a multiplicative range, in a range u plus? That's the question, right? Because if you can prove that the determinant is outside a constant range, not a polynomial in n range, a constant range is all we're trying to prove, but after roughly n squared over log n queries. And the answer, I'll try to explain this, is that this set, the set of matrices whose determinant is in a small range, is in fact very far from being a product set of matrices. And I'll quantify what we mean by far, but that's the intuition, that a product set is this very specific structure. However, if you restrict the determinant to be in a small range, you cannot be close to a product set. Okay, now to see a very special case of this, what if we restrict the determinant to be exactly the same number, okay, a particular number? So let's say we restrict the determinant to be a constant u, and each row of the matrix is chosen from some convex set. Now in this case it's an easy induction that there exists an ordering on the rows, on the sets, so that for this to be true it must be the case that R1 is a single point, R2 is a translation of this line, the line to the origin, R3 is a translation of this plane, and so on. Okay, and that's easy to see. Suppose you pick R1 okay first. So the only sort of formula that I'm using to this proof, the formula for the determinant, is just that the determinant of a matrix can be written as the product of the lengths of projections. By that I mean where Ri tilde is just the projection from of the matrix R onto the span of the first orthogonal to the first R minus 1 rows. Okay, so all we are doing here is, look, you can compute the determinant as follows. It's the length of the first row times the length of the second row after it's projected to orthogonal to the first row, and so on. And so here it's the determinant will be the length of this row times whatever you pick for the second row after it's projected orthogonal to R1. Now if it's a 2 by 2 matrix, that better be a single point in order to get the determinant a constant, and therefore its lifting in the original space must be, all it can be is a line parallel to this. So it takes a little more work to prove the full statement, but it's a very special set of matrices that can be a product set of, that can be a determinant, constant determinant. Okay, so now the question is, what about when the determinant is in a range, u plus c? Now this is a little more tricky, because so for let's just say 2 by 2 matrix, 2 points in the 2-dimensional space, I just said, look, the first point, one of them has to be a point and the other one has to be contained in a line. Okay, because when you pick this and project orthogonal to it, you better get a single point. Now if you're talking about a range, we lose this asymmetry. In fact, this could be in some range and this could also be in some range. but you do get a condition which says that the product of these lengths is bounded by some constant. Okay, constant that depends on the range. So so the condition for 2 by 2 is that the product of these lengths is so it cannot be that both are large intervals. Okay, or large sets. And you also have this here. So in general, actually, this observation can be extended as follows. Oh, so that's what I was saying for the determinant formula. So just looking at this formula, if I look at the last row, let's say I pick the first n minus 1 rows randomly, then the projection of then the last row must lie in whatever is the target range times the part of the formula we've already computed. Okay, so it's the same multiplicative range. Okay, but what does this mean? It lies on a small segment, so the projection orthogonal to the n minus 1 dimensional space is some line, and on that line it lies in a segment. Therefore, in the original space it lies in some band. Okay, so you already get that each row, you could apply this in any order. The formula is independent of the order. So you get that each row, the set must lie in some band. Now, if you extend this to pairs of rows, using this two-dimensional lemma, this can about how these sets relate, you actually get a pair of bands for every pair of sets, and this restricts the regions to lie in parallelepipeds, whose product of volumes is bounded. So here is one way to characterize this precisely. There is a constant C, universal constant, such that for any partition of the ball of radius root n to the n, so that's the initial set of matrices we were starting with. So take any partition of this into no more than 2 to the n squared minus 2 to the n squared over 4 parts. So any partition of this product set of matrices, so that it where each part is a product set. Okay, so we're doing some partition where each part is a product set. There exists a subset. We're missing that. There exists a subset whose volume is at least half of the full volume, and for any u, now this is a scalar u, and a point random from any one of these parts in the subset, the determinant does not lie in a constant interval around u with 1 over polynomial probability. So I've got some partition into product sets of matrices, and then look at a subset of volume half of them. Now pick any one of these, pick a random matrix, and its determinant will not lie in a constant range with 1 over polynomial probability. That's the determinant dispersion lemma that drives the volume lower bound. So that's I just have a concluding slide now. Well, so this dispersion I would like to investigate more to see if it actually can be cleaned up some of the made into a general tool for proving lower bounds. The variance conjecture is nearly tight for convex polytopes, and it would be nice to resolve the upper bound. At the least, it would give a faster volume algorithm. The volume problem itself,
Variance conjecture would give a faster volume algorithm?
yes, it would improve the complexity by square root n. Yes, so the variance conjecture is weaker than the hyperplane conjecture, which I mentioned earlier, and this variance conjecture by itself, and that was the reason we thought about it in the first place, it would improve it from n to the 4 to n to the 3.5. But as in the past, the volume problem has led to some nice things, in this case techniques for lower bounds, and so the one question that's remaining is the answer n squared or n cubed? I mean, this is true if the conjecture is true, and this is what we have right now, ignoring the logs, so it would be nice to resolve this. Now if the lower bound is actually better, one would have to use a class of bodies that's more complex than parallelepipeds, because for parallelepipeds n squared is the best you can prove, so I don't know what's appropriate. There is some chance this can be used to get circuit lower bounds, I mean we can think of the oracle as some kind of threshold gate, and maybe for the determinant one can prove an n squared lower bound on the number of. So this is just a vague idea at this point. Here is a more concrete implication is for property testing. So
lower bound, but what would be the allowed operation? So
thresholds.
Yeah, still you would want to allow only thresholds.
Yes. I mean I'm trying to make the oracle, what we have in the oracle right now, a gate. The difficulty is that right now the oracle accesses directly the input, whereas in a circuit you should be allowed to do operations on the results of previous operations, so which is non-trivial. Now for property testing more concretely, here is one theorem. Suppose I have a matrix and you'd like to determine whether its determinant is in some small interval, constant range interval. How much of the input do you need to see? It's a randomized algorithm, so it might choose some subset of the matrix, calculate something, maybe see something else, and then say this is my guess. Now how much of the input matrix do you need to see? And so what this the previous lemma that I put up directly implies is that you need to see, you get rid of the log n in this case because the oracle is just looking at individual entries of the matrix, and then you actually need to see most of the matrix, 1 minus epsilon times n squared for any epsilon greater than 0. Similarly for some other related problems, but this is probably the most interesting one. So I'll stop here.
Are there other models for accessing convex bodies in which the results look different?
Okay, very good. So in fact a stronger oracle for convex bodies is a separation oracle, where in addition to being able to ask is the point in or out, if it is out you also get a separating plane, a proof. So in this case the lower bound doesn't apply. For a parallelepiped, I mean you just need n queries to figure out the whole thing. Every time you ask you get a plane that gets it. So and as far as upper bounds are concerned in that model, it's not clear that you can do better than what we have with just the membership. So
The bouncing.
yes, so there is a conjecture that there is this walk. There are certain random so the upper bounds are all based on random walks. I gave the whole talk without saying the word random walk. But the upper bounds are all based on random walks, and to implement the ones that have been analyzed, you only need a membership oracle. At each step you want to know whether you're in or out. But in fact a certain natural walk can be implemented where you choose a random direction and you want to go, let's say, a certain distance, but if you encounter a boundary you reflect off the tangent. Now to implement this can be naturally implemented using a separation oracle, but there is no clean way to do it if you just have membership. I mean there's an overhead if you wanted to convert to, you can convert membership to separation, but there's an overhead. So that walk as far as we know is actually faster, might even be linear in n, n times polylog to sample, and then the upper bound would come down potentially lower. So it's an interesting question for the separation oracle, both upper bounds and lower bounds.
So it seems that to prove something about the dispersion, you can deduce it if you know the second moment and the fourth moment.
Okay.
So I wonder, I mean, is it difficult here, for example, to try to compute?
Yeah, you might be able to do it, but it seems to be at least the same order of difficulty as directly establishing the dispersion. For the matrix case, actually, for the volume lower bound, I have not been able to compute the variance, and I stopped halfway because it wouldn't imply the answer anyway. So computing the variance is not an easy thing. But for the product of the lengths, maybe in fact the fourth moment is not too bad, but it's not clear. Yeah.